Can the Godot engine handle a truly massive open world? This is a question many developers ask. It is a critical question for anyone dreaming of building vast, explorable spaces. I decided to find out for myself. I would not just talk about theories. I would push the engine to its limits with real tests. My goal was simple. I wanted to generate real benchmarks and see what broke. I wanted to understand exactly where Godot's strengths and weaknesses lie when faced with the extreme demands of an open-world game. This essay will document that journey and share what I learned. First, we need to define what a massive open world really means in this context. We are talking about a very large map. It could be dozens or even hundreds of square kilometers. This world is not empty. It is filled with thousands of objects like trees, rocks, buildings, characters. To run smoothly, such a world requires advanced techniques. The engine must intelligently load and unload parts of the world. This is called streaming. It must also simplify distant objects, a technique known as level of detail or LOD. Godot is a fantastic open-source game engine. It is celebrated for being free, flexible, easy to learn. Its node-based scene system and user-friendly scripting language, GDScript, make it a favorite for indie developers. But creating a large-scale, open world is one of the toughest challenges in game development. This task tests the absolute limits of any engine's capabilities. My tests would focus on terrain size, object counts, memory usage, draw calls. I would measure performance, identify the bottlenecks, and explore the workarounds that make it possible. The core of this investigation is to provide a practical guide. I will show you the numbers from my tests. I will explain the fundamental concepts you need to understand, like terrain tiling and object batching. We will look at simple code patterns that beginners can grasp. The first and most significant challenge is the terrain itself. The most straightforward approach is to create one single, gigantic mesh for your entire world. You model the terrain in a tool like Blender and import it. However, this is a recipe for disaster. A single massive mesh consumes an enormous amount of memory. The graphics card has to draw every single triangle of that mesh, every single frame, even parts miles away. This results in terrible performance. Break the terrain into smaller pieces, tiles, chunks. Imagine your world map is a giant grid. Each square is a separate, smaller terrain mesh. Visual: top-down grid with central 9 squares highlighted. This is the foundation of world streaming. As the player moves, the game only loads the tiles immediately around them. Tiles far away are not loaded into memory. This saves memory and reduces triangles the GPU must process. This is the only viable path for a large world. Godot is well suited for this tiled approach. Its scene system is perfect for it. Design each terrain tile as its own packed scene. Write a streaming manager script to load and unload scenes as needed. Use Resource Loader to load scenes in the background. Background loading prevents freezing or stuttering when new world pieces load. Small, manageable tiles are the first step to a performant open world. I started with a single 4 kilometers by 4 kilometers terrain mesh. The frame rate was unplayable, below 15 FPS with a basic texture. I switched to a tiled system with 64 tiles. Each tile was 512 meters by 512 meters. With only the 9 tiles around the player loaded, FPS jumped to a stable 60. This simple change shows the power of streaming. Do not use a single mesh for your world. Build your world out of tiles and stream them in and out. Godot doesn't include an automatic LOD generator. You can't just import a model and have Godot make LODs for you. But Godot is flexible. You can build your own LOD system. The common approach: write a script that checks camera to object distance and swaps the object's mesh accordingly. Within 50 meters, show high detail, 50 to 200 medium, beyond 200 low. This applies to everything in your world: trees, rocks, buildings, characters. For very distant objects, you might use 2D billboards. Flat images that always face the camera. It's an extreme LOD with massive performance gains. You can also LOD materials, use simpler shaders at distance. Distant objects can use much simpler shaders, without complex lighting, further saving GPU time. Building LOD is about creating a convincing illusion where it matters. Side-by-side detailed rock versus low-poly rock. My tests showed the dramatic impact of LOD. I placed 1,000 detailed tree models, each with 8,000 triangles. Without LOD, the frame rate dropped to about 25 FPS. I made 2 simpler versions: medium, 1/500 triangles; low, 300 triangles. With a distance-based mesh swap script, the frame rate jumped to over 60 FPS. The visual difference at distance was almost unnoticeable, but the performance gain huge. You must implement LOD for your open world in Godot. Section 4. Populating the world, mastering instances with multi-mesh. An open world can feel empty without dense vegetation, rocks, other repeating details. Placing thousands of individual tree nodes, thousands of individual grass nodes is a terrible idea. Each node in Godot has an overhead cost. Thousands of nodes will slow scene processing and create thousands of GPU instructions. Those are draw calls. GPUs prefer fewer, larger instructions rather than many small ones. Too many draw calls equals a severe bottleneck. Godot has a solution. Multi-mesh instance. Multi-mesh draws thousands of copies in one draw call. Very efficient. Define a base mesh, single tree, clump of grass. Tell the multi-mesh to draw it many times and provide position, rotation, scale per instance. Perfect for dense forests, fields of grass, scattering rocks. Setup is straightforward. Create a multi-mesh instance node. Assign a multi-mesh resource. Assign the mesh to duplicate. Set number of instances. Place instances via script or a helper tool. Example, scatter trees randomly across a tile. Avoid steep slopes. Avoid water. Section 5. The rendering bottleneck. Draw calls, batching, and lighting. We have already discussed how multi-mesh can drastically reduce draw calls for repeating objects, but you still need to manage draw calls for unique objects like buildings, bridges, special landmarks. One key strategy is to use as few unique materials as possible. If two objects use the exact same material, some graphics APIs let the engine render them more efficiently. A very effective technique is to use a texture atlas. A single large texture containing many model textures. Share one texture and material to help the engine optimize. Godot 4 can help with OpenGL3 batching. Enable it in project settings, and the engine will group mesh instances, sharing material properties into fewer draw calls. Great for many small static objects. Example, a village with many small props, barrels, crates, fences, all sharing one material. Batching helps. Enable the setting and test performance for your scene. Lighting is another big performance cost. Every dynamic light with real-time shadows is expensive. Hundreds of dynamic lights will destroy your frame rate. Use them sparingly. For static lights, bake lighting. Baking pre-calculates lighting and shadows into a light map. At runtime, the engine just displays the light map. Very fast. Godot's Light Map GI node handles this. Dynamic objects like the player or NPCs need more. This is where Reflection Probe, Voxel GI, and GI Probe nodes help. They capture baked environment lighting and apply it to moving objects. High-quality GI without the massive cost of many real-time lights. My tests confirmed. One dynamic sun with Lightmap GI ran at 60 FPS. Adding 10 shadow casting point lights dropped it nearly by half. So, be careful with real-time lights. Section 6. The Unseen Engine. Physics, AI, and Smart Scripting. Performance is not just about what you see on screen. The unseen systems running in the background, like physics and artificial intelligence, can also consume a lot of CPU power. In a large open world filled with thousands of objects, running a full physics simulation for every single one is impossible. Just like with rendering, you need to be smart about what you simulate. Objects far from the player do not need active physics. Disable simulation entirely and re-enable it when the player gets close. Collision shapes matter. Godot can generate a concave polygon shape from a mesh, perfectly accurate, but very slow. Fine for static geometry, but never use it for dynamic objects. Use simple primitives, spheres, boxes, capsules, combined to approximate shape. This is far more efficient for the physics engine and results in better performance. AI is another potential CPU hog. You cannot afford complex pathfinding every frame for every NPC. Implement an update scheduler. Nearby NPCs tick 10 times per second, farther ones once per second, very distant ones disabled as data until needed. This spreads the CPU load over time and keeps the game from stuttering. GD script is incredibly easy to use, but it is not the fastest for heavy math. If a specific part is a bottleneck, Godot gives options. Rewrite the performance-critical module in C# or C++ using GD extension. My tests on pathfinding showed C# 2-3x faster than GDS script and C++ over 10 times faster. Use GDS script for general logic but switch languages for the heaviest tasks. Well, it's worth profiling first. Section 7, Conclusion. The verdict on Godot for open worlds. So, after all these tests, what is the final verdict? Can Godot handle a massive open world game? The answer is a clear and confident yes, but you must be willing to build for it. Godot is not a one-click, open world solution. It lacks specialized out-of-the-box tool sets. It gives you fundamental building blocks. You are the architect who must assemble them. You will need to build your own systems. Success hinges on the core techniques we discussed. World streaming is mandatory. Break your world into tiles, load tiles dynamically, level of detail for meshes, level of detail for materials. You must master the use of multi-mesh. Populate with dense foliage. Populate with objects. Protect your draw call budget. Be strategic with lighting. Bake static lighting. Use real-time lights sparingly. These are the pillars of performant open worlds. Main limitation, fewer high-level tools. You'll write a terrain streaming manager. You'll write distance-based LOD scripts. Leverage community plugins and tutorials. It requires more hands-on work. The benefit, ultimate flexibility. Tailor systems to your game. You're not locked into a black box. Start small. Optimize from day one. Build a single terrain tile. Test LOD systems. Test multi-mesh systems. Use Godot's built-in profiler constantly. Is it the CPU? Is it the GPU? Is it draw calls? Is it a slow script? Fix one bottleneck at a time. Careful design. Smart optimization. Willingness to write system-level code. With that, Godot can bring your massive open-world dream to life.